In this example, we want to test whether some observed numbers for a particular trait in some offsprings follow actually a Mendelian inheritance. And for that, we can use a goodness of fit model. So what have we got here? We have been given that we cross two homozygous parents, capital A, that is the dominant allele, and lowercase a, which would be the recessive allele. And we take the offspring of these crosses and cross these offspring. So what have we got? Well, obviously, when we cross the homozygote parents, if we do something like that, inevitably our offspring in the F1 generation will be capital A, lowercase a. And now we can cross these offspring and get the F2 generation. So for the F2 generation, we will get the following pattern if we cross that. So we have uppercase, we've got uppercase, lowercase, we've got uppercase, lowercase, and two lowercase here. So our Mendelian inheritance pattern, when we look at the number of offspring that we would expect, would be we get one homozygote for the dominant gene and the same number for the heterozygote, for the homozygote recessive gene, and we've got two of the heterozygotes. So in this case, we would expect a typical monohybrid inheritance pattern with a 1:2:1 ratio. And now we need to check whether these observed numbers that we have here actually fit this 1:2:1 pattern that we would predict with this monohybrid inheritance pattern. And what we need to do is, in the first place, we need to formulate a null hypothesis. So we need to write down a null hypothesis. And this null hypothesis basically gives us an indication of how to make a decision. So the null hypothesis, a valid null hypothesis, could be there is no statistically significant difference between observed and expected values, and any differences that we see in these observed and expected values, they can be explained by sampling error only. And an alternative hypothesis, which we sometimes call H1, would be there is a statistically significant difference between the observed and expected values, and the differences that we observe between observed and expected values are due to sampling error, because we always have sampling error, and an additional factor, which in this case would mean actually there is something different to this 1:2:1 distribution of the data. Maybe it is not a monohybrid inheritance, maybe it's not just Mendelian, maybe there are some other factors which we don't know. We just simply would see if there is something different. So we formulated our hypothesis. We would set a significance level alpha. So our alpha, that is the type 1 error level. We very often set this to 5%, or that's the same as 0.05. And we would make a decision rule where we look at the p-value that we calculate, and to, as a sort of jog your memory, the p-value is the probability to observe a test score if the null hypothesis is correct. And we can say that if the p-value is smaller than our significance level alpha, we would reject the null hypothesis. Remember, if p is low, h null must go. On the other hand, if the p-value is larger than alpha, then we would fail to reject the null hypothesis. Fail to reject the null hypothesis. So we would more or less accept the null hypothesis, whereas in this case we would say the alternative hypothesis is correct. So what we need to do now is we need to calculate our test score, and we can use a chi-square goodness of fit. And just to remind you how we can calculate that, there is this equation where we sum up the observed data minus the expected data, square it, and divide it by the expected data. Now, of course, we've got our observed data, but we need to figure out what are the expected data. So how can we actually do this? So first of all, what we do is we sum up the data, all our offspring that we have, and we do this with the sum function equals sum in Excel. We could add them all up, but since we are in Excel already, we do the sum function. So we've got 659 offspring. That's the total number of offspring that we have. 659. And we know that of these 659, 1/4 of these 659 would be homozygote dominant. So we could calculate 659, 1/4 of that would be homozygote. Likewise, 1/4 of these 659 would be homozygote recessive, and 2 out of 4 of these 659 would be heterozygotes. Now what we can do is we just simply calculate these numbers. So equals 659 divided by 4. That's this number, 164.75. That is this number here for the homozygotes, and of course for the heterozygotes we have 659 divided by 2. In this case that gives us 329.5. So these are now our expected numbers. So expected numbers. And we can now do our test score. So the chi-square score here, we can write this out. We would say in the first place we've got 158. That's our observed, minus 164.75 squared divided by 164.75. That's the first one. Plus for the heterozygotes, we find 350, that's the observed, minus 329.5 squared divided by the expected, that's 329.5, plus for the homozygote recessive we have 151 minus 164.75 squared divided by 164.75. And we can do this calculation. We can either do that in Excel or in a calculator. And if my calculation is correct, we get a chi-square value of around 2.7. So that's our test statistic. That's this chi-square value when we do this calculation. And now we need to convert this chi-square value into a p-value. And for this we can use a very handy Excel function that does exactly that. It converts a chi-square value into a p-value. And I put that here. We start typing equals chi-square, and we are looking for the dist RT. That's the second one here. Dist RT, chi-square dist RT. It asks us for the chi-square, our test value that we just calculated, so that was 2.7. And we need to figure out the degrees of freedom. Now the degrees of freedom is just simply the number of columns that we have minus 1. So degrees of freedom, let me write this here, degrees of freedom equals columns, or I should say row in this case, rows minus 1. So we've got 3 rows minus 1, that would give us 2 degrees of freedom, which we just simply put in 2 degrees of freedom, close the bracket, and we get a p-value of 0.259. So that's our p-value of 0.259. And now we can go back to our decision rule that we made up here, and we will find that this p-value is larger than our alpha, larger than 0.05, which means we fail to reject the null hypothesis. We say there are no true differences between the observed and the expected values, and therefore our conclusion is that the observed numbers actually support the assumption that we've got a 1 to 2 to 1 monohybrid inheritance, which is perfectly in line with Mendelian inheritance. So I hope this makes sense, and thank you very much for